Well, good day, everyone. Great to meet you. As mentioned, so I'm a senior solutions architect at NVIDIA, and sort of my main job is to get models to production. And if folks are using the big box APIs, you'll understand how those work at a very high level. If you're using your own language models, you'll understand all of the things that you need to take into consideration when you go to production. I saw people from all over the world tuning in. I didn't see anybody from the Caribbean, so if you're from the Caribbean, shout out. That's good. So high level, think of 5 buckets that we may cover. First is this theory overview, giving you a high level view as to what happens when a prompt comes in until a prompt comes out of a large language model. And we'll talk about speed, and Cal will touch on optimizing these models for production so you reduce your cost of deployment. Next, we'll talk about exactly what happens to a prompt when it goes into a language model, and then what ends up happening as you start generating tokens. They're typically sort of 2 different phases. After that, we'll talk about how you start managing memory on the GPU, or things that consume your GPU memory when you're doing LLM inference. After that, we'll talk about measuring LLM inference performance, some metrics for you to look at. They'll be very high level. Feel free to reach out to us if you want to get really deep into the weeds. And then I'll touch about some things on optimizing LLM inference. Okay, jumping into the theory, super high level. What is inference? And I think it's good to take a step back. If you don't know what inference means, it's just getting an output from a model given some corresponding input. And I put many different types of inputs, even though we're talking about LLM inference today. I think what you'll end up seeing happening sort of over this year and next year is this multimodal type inferencing, where you're going to be pushing a lot more data into these models to try to get some corresponding output. That output, as you're seeing on the right-hand side, could be text, image, sound waves. Some people work on molecules. They're predicting molecules for drugs, et cetera, et cetera. Some people might start doing prices. Who knows? We're getting videos. You're getting 3D designs. Lots of things that are happening in the inference world. So as you think about charting your own positioning in your data science career, inference is a great area to become an expert in. Now, let's jump into LLM inference. So on the left-hand side, I'm asking this large language model to write me this presentation that I'm showing to you today. I want you to think I'm really smart so I can keep my job at NVIDIA. But at a high level, what happens? I send this prompt into a GPU. Notice there's nothing in the box in the GPU. We'll start to fill that out as we go along in the presentation. And then on the right-hand side, you're seeing I have LLM inference is a tough topic to understand. And I put these staggered just so that you can keep in mind that these are different time steps. So when this model generates its first token, LLM is the first token. And on the bottom here, I'm putting every output token that is generated gets pushed back into the initial prompt. So as you think about what is the total number of tokens that a model processes at over a total request, it's going to be all of the tokens that are coming in addition to all of the tokens that are coming out. So when I do LLM, I'm going to pass LLM back inside, and then that's going to give me inference. And then I'll take LLM inference, pass that back inside. Typically, you only pass the current token that's generated back into the model so that you can get a new generation. So hopefully that makes sense at a very, very high level. So here are the actual blocks of processing that are happening. Once again, I try to keep this a little high level. I do abstract some of the more technical terms. Initially, you'll see me start to introduce some of the technical terms coming in. So first, you saw this prompt before. We're going to tokenize this prompt. Tokenize just means putting it into a format that a machine learning model can understand. No machine learning model natively works on text. It typically works on, vectors of numbers, so we can do a bunch of math with the data. So if I'm in an image, I'll come to some vector or matrix of numbers. If I'm text, I'll come to some matrix of numbers or sequence of numbers. If I'm, a molecule, I'll come to that same sort of type of sequence of numbers. So then I can do a bunch of linear algebra. Once I get onto the GPU in this particular vectorized format, I'm calling this thing initial prompt processing. So if you send 100 tokens, or you send an entire document, it could be 1,000 pages, something ridiculous, you're going to have to process that prompt. And that language model is going to have to understand exactly what it is that you're asking. And that's through the attention mechanism. So you'll get to see a bit more about what that means. And from there, once it understands your initial prompt, it's going to say, okay, now I'm going to start answering you and generating tokens. And you'll understand how that's a sort of iterative process. It's not something that you can really speed up and sort of do in bulk. And then lastly, once you get that token is just literally a number. You need to associate that number with some human text or human data that the end user will understand. And we're calling that detokenization. And that's how I get out, the spew of English words in this case. And keep in mind, as you think about, let's say, doing LLM inference on different languages, you will have different types of tokenizers that will tokenize your text and detokenize your text. So that's something to keep in mind. So digging into the tokenizer, I know if a lot of you are sort of do this every day, you live with tokenizers a lot, but I just wanted to make sure that it was covered. So first, that prompt is coming in. As you're reading here, your goal is to take text and put it into some meaningful vector of integers. And that vector of integers has some index to a vocabulary. And every single language model has some vocabulary that it was trained on. I think Llama 3 is 128,000 tokens. So tokens are not necessarily words that we might read directly. Think of it as the best segmentation, the best number of building blocks that can reconstruct the entire training data set very efficiently. So it's not necessarily words like you see here on the page. I'm saying each token in that vocabulary has a corresponding integer. Think of a lookup table. If I see the word convert and that had an entry into the vocabulary and that entry was 10, I'll literally just replace the word convert with 10. So that's what you're seeing. A good barometer for you to think about when you do tokenization is that every token that an LLM has, maybe approximately 4 characters, that's just a heuristic. So in case you have, I don't know, 10 pages of documents, you know the total number of words or characters, you can estimate how many tokens might actually exist on the GPU itself. I'm claiming this vector is a total vocabulary of words. I go from T1 to Tn, and it's just the total number of words in vocabulary. And then here are the corresponding indices if I were to map each of those words. And then on the bottom here, I'm saying, okay, make me sound smart or make me sound smarter. And I'm just assigning some random indices to each of these words. I'm considering each of these words as a token. So as you think about pushing your text into a language model, your understanding of the actual vocabulary of that language model becomes very important. Because if I put in a series of text that this tokenizer doesn't understand, it doesn't actually get mapped to something. It gets mapped to typically an unknown token on the inside, and that could sometimes mess up your results. So hopefully tokenization makes sense at a very high level. Remember, we're not working on text, we're working on these vectors of numbers or matrices of numbers as you start to accumulate things in a batch. Okay, jumping into prompt processing and token generation. So we see now we're going to focus on this initial prompt processing box. This is known as prefill. So if you read a lot of research papers and they're talking about the attention mechanism and doing these types of things, the stage at which the language model understands your prompt is called prefill. So just keep that in your head. So now that's going to take some tokenized input sequence, which is taking a vector of numbers that represent the entire sequence that I have, and I'm going to compute this thing called the attention mechanism. What I'm saying here is that the attention mechanism typically takes an individual token and tries to understand how does this token or this word or molecule, whatever the case may be, how does this unit relate to all of the other units in the sequence? So this is how, when it goes to predict a word, it understands, hey, these were the words that were related to this word that I might predict. So it has this notion of understanding what is important in a series of tokens. And the relation between tokens is very important, and different models will map or interpret that relation in different ways. This is why you see so many different types of language models. They were trained with different types of attention and different mechanisms to learn all of the weights, and we'll see the weights coming up. It's okay if you don't see a ton of diagrams, nor understand what attention means at this point. I'll describe it coming up soon. You'll see this term called attention head. I'm encouraging you to think of it, just think of it as a module. So this attention head or this module is going to compute attention or find the relations between words in a sequence, but it's going to have its own sort of knowledge, and that'll make sense coming up. I'm saying LLMs have multiple attention heads, so they'll have multiple of these modules that will then go try to interpret the data in different ways. Think of it as if I asked a physicist to interpret the text, I asked a chemist, I asked a biologist. Think, that's an abstracted notion of what an LLM attention head is doing, but um, keep in mind that these language models will learn sort of these sets of abstracted relations. And um, that sort of ends there with each attention head is sort of relating the text very differently. Okay, so let's look at what's happening under the hood. So I said, all right, I gave you 2 words or 2 tokens. So my sentence in this case is two words. So I converted that to some vector representation. When you start looking at parameters in a language model, just a shout out Jay Alama, if you have not seen his tutorial on the illustrated transformer, I think it's one of the best tutorials out there. And as you think about what's happening on the GPU, this is my new representation of my sentence. So I have 2 words in the sentence. And then I'm going to do this matrix multiply against the weights of my model. So the weights in an LLM, you'll typically see WQ, WK, and WV. So I'll explain what that means. Sometimes when you look at papers, you'll see Q, K, and V. So if you look on the right-hand side, I'm saying this attention mechanism, so some math that I'm doing, I'm calling this math attention, is going to involve the matrix multiply of this Q times this matrix K transpose. Then I'll do that against V. And this D of K is just, hey, the length of that vector, and I'm going to sort of renormalize or scale the numbers in there. But what I want you to take away is that every time you see a vector times a matrix multiplication, that's called a projection, meaning I'm sort of asking the model, how are you interpreting this data? That's what the output of that means. So this Q, if I pass this X times this WQ into this Q matrix now, these are called your queries. So this is called your query key and value matrices. You'll see this a lot if you, interact with any type of attention papers and stuff like that. And I'm highlighting this thing called KV cache. So I'll touch upon that. Think of that as your LLM's memory. But overall, what this is trying to do is to say, these input tokens come in, I get this Q matrix. When I do this Q times K math, that's actually saying how does a token relate to all other tokens? So I get some sort of distance measure between one token and another, and then I'm going to use that distance measure between tokens to do a weighted sum. So if I took a bunch of vectors and I said I'm going to take 5% of this vector, 10%, 0%, 1%, and add them all together to get a single vector, that's essentially what you're doing when you compute the attention head. And this output of the attention is typically sort of the same size as this Q input that you have coming in, and that's passed off to what's called a decoder to try to predict what is the next token. And when you think about, hey, what is the next token and I'm going to predict given some input, that token comes from some vocabulary, and that vocabulary, that prediction would have said, hey, okay, the 5th token in my vocabulary was the most probable to get chosen as the next token. So hopefully that makes sense of what attention is. I'm going to show you a more complicated slide, but hopefully it'll transfer over. So once again, I have this sentence thinking machines. This is taken directly from Jay Alama's tutorial, so definitely go through it. I embed the word. Remember, I'm just converting it into some vector representation. And from there, I'm going to essentially, in doing this matrix multiply, each of these attention heads, so remember this Q, K, and V matrix. So now in this case, I have 8 attention heads. So I have 8 groups of these model weights that I'm going to use. And when I do this matrix multiplication, that's a projection. And these are the interpretation of the language model. How does the language model see my tokens that are coming in? That's essentially what's happening. I leave out some details on things such as positional encoding and stuff like that, so you can go read more about that. But what I want you to just take away from here is that I have my input data coming in. I do this matrix multiply against these 8 sets of matrices, or these 8 sets of weight matrices, essentially is what you should think of it. I get these 3 output matrices, and think of this as the 8 different experts in this LLM interpreting my input data, and here is their interpretation. I compute the attention mechanism, and then typically, this is for multi-headed attention, there's typically another set of weights that will learn during training. Also keep in mind that these weights were learned during training as well. This is what, when you download a language model, this is kind of what you're downloading, these weights here and here. And then this final weight matrix is going to combine all of the experts. I'm saying experts very loosely, but it'll essentially combine all of those to get, here's my final interpretation. Here's the final interpretation that the language model has of your text. But this is just high level of the high level interpretation of attention. So hopefully that makes more sense. And that's where language models really get a lot of their smarts from. So once I finish this attention, I sort of understand the token. The LLM now understands the sets of token or token that I just took in. Now I'm going to decode. All that means is that I'm going to call this the decode and generation phase, but notice the difference between this box and each of these individual boxes here. So I'm going to produce a token one at a time. That's what I'm saying in this first line. And when each token is generated, that comes from this initial prompt processing. When I get a token, I'm actually going to push it back inside. So it'll almost think of it as it's expanding the initial prompt processing piece. And from there, I'm going to use these key and value matrices. So these key and value, after I did this matrix multiply, I'm going to use those. And that's what's actually stored on a GPU. You'll see another view of it sort of coming up soon. And from there, once it understands, it has all of the tokens, it'll generate sort of a probability mapping against your vocabulary and say, I don't know, these top 5 tokens are the most probable, and then it'll choose. There are different decoding mechanisms that you can choose on the output. But the main thing to take away from the decode phase is that it is generating a single token at a time. And every time that token is generated, it goes back into the input, and essentially you're storing all of that data onto the GPU. Here's another view. This is a good article to read on mastering LLM techniques for inference optimization. It's a blog from NVIDIA. And hopefully these 2 words make sense to you, this thing called prefill and decode. And the goal is to try to speed up the decoding phase. Because remember, I'm saying I'm generating a single token at a time. GPUs like to generate or process a ton of data at once. So when we're generating 1 token at a time, we get kind of eager. We want to process more. So these matrices should make sense. So these are the query matrices. This is your input data multiplied by that WQ matrix. These are your key vectors. These are just your input data multiplied by the key weight matrix in your model. And then your values, that just data multiplied by your values matrix. So these are the outputs. And then I get this interpreted result. So when I decode, instead of passing this new generated token and all of my initial prompt again and reprocessing it, I'm actually just going to keep the K and V value matrices, because when you go to compute your attention, the language model needs to understand, how is this new token that I just generated related to all of the text that I had before? That's the sort of intuition you should have in your mind. And in order to do that interpretation is just a bunch of vector matrix math that's happening. So I keep around all of the LLM's interpretation, that's a K and V matrices. I keep around that interpretation so I can quickly do this math in order to actually sort of move forward with processing the next token. So hopefully that makes sense. Taking a step back, looking at this from left to right, sort of follow my pointer so you don't get lost with some of the things. I have an initial prompt. I'm going to sound really smart after this prompt gets processed. I tokenize that data. So I go from text to some vector representation. That vector representation comes in. Now, this is where I want you to pay attention. On the GPU, in terms of things that pick up space, my model weights are going to pick up space. We talked about this prefill stage. This is you processing the input prompt that's coming in. So that's going to occupy a particular amount of memory on the GPU. Once I understand the prompt, I'm going to start decoder generation. So I'm generating those tokens. But when I generate a token, I push it back into the GPU. In order for the human to understand what I decoded, the output of the LLM, I have to decode it back to the original input data. And when I continue go through this loop, I'll stop. Usually it's a max token, or the model itself will predict this end of sequence or end of token, excuse me, yeah, end of sequence character, and then the model just stop, and we're done with that request. On the bottom here, I put some things for you to keep in mind. So as you think about cost of your LLM deployment, this is for folks that run very, very large models like OpenAI, Gemini, Anthropic. This is all the same theory that they're running. When you pass in a huge prompt, now that you understand the amount of data that you push into the GPU, it gets stored and needs to be stay there on the GPU. So if I send, I don't know, 10 pages of text, that's going to occupy more memory on the GPU. This is why when you look at the token pricing, you typically see your price on the input and the output as well. So a larger input coming in will have a larger KV cache. I'm calling those key and value vectors that I mentioned before. That's known as your KV cache. So you should expect the longer the prompt, the longer the time to first token. I will talk about time to first token coming up. But this stage actually occurs very quickly on the GPU because the GPU can do math very quickly. So that's why you don't have to wait too long to get that first token coming out. And then on the top here, I'm just reminding you that you're generating one token at a time. It is the slowest part of the inference, but hopefully that makes sense. So I wanted to talk about GPU memory and what's filling up that GPU memory. So what I'm saying here, I have my model weights. This is a single request. I had that prefill stage that I spoke about, and then all of the tokens that I generated. And then as you start thinking about a production deployment, what that's going to do to you is each request that you have is now going to have its own prefill or its own KV cache and all of its respective tokens. So when a new request comes in, if the GPU memory is occupied with all of these tokens, you typically see a delay in that request being processed. So that's what you have to keep in mind when you deploy deploy LLMs on GPUs. So here, all I'm putting is 4 different types of input and output size prompts that you have coming in. Give me 1 second. And so I'm saying, okay, if I push in a long input and I push out a short output, I generate a small number of tokens. My model weights are typically constant on the GPU. A nice trick for you to remember is multiply the number of parameters by 2, and that's your number of gigabytes in FP16. So if I do a 7 billion parameter model times 2, it's 14 gigabytes on the GPU in FP16. I send in a large input prompt. So that means my prefill stage will be big. That's why I'm sort of filling it out here. My output is short. So I have, I'm representing this as a short set of decoding tokens. So this is the amount of memory I have free to process everything else. Now, if I look at, this is the stage where it will, I think, be most expensive in an LLM deployment, where I have a long input and a long output. What does that mean? My model weights are constant. My prefill stage is bigger and my decode stage is bigger. And same thing here, if I pass in a short input, my prefill stage will be small, but I have a long output. I'll occupy the memory with generated tokens. And this is good segmentation for you to keep in your mind as you sort of start to model and to monitor very large deployments of GPUs with LLMs. And then lastly, this is the best one. It picks up very little space on the GPU. It can get processed very quickly. And I'm just going to walk through sort of what's going to happen to you as you do some of these things. So the first thing to keep in mind as you measure things is your time to first token. So how long does it take to process this prompt and get the first token coming out? I would have to go through this initial prompt processing or pre-fill stage, process the prompt, generate my first token. This is something you should be measuring in your deployment. Inter-token latencies, all this means is when I start generating tokens, I want to look at the time it takes in between each token, because sometimes that's a very good measure as to the performance of your system. Remember, in an LLM deployment, you have multiple requests just coming in from a bunch of different people. And the rate at which you generate tokens should be constant if your system is performing really well. Lastly, your total time to generation. How long did it take you from when the prompt started all the way till you finished generating all of the tokens that you were supposed to return to the user? There's actually a lot of different things that you can measure to sort of optimize your deployment in terms of memory and cost. We always try to reduce the cost of inference here at NVIDIA, so something to keep in mind. I just wanted to walk you through, you've seen some of these plots before, but I just want to walk you through exactly what's happening in each of those boxes. So when I pass in a long input and I get a short output, I would expect my time to first token to be longer because I had a bigger prompt to process. My KV cache is the amount of tokens I'm storing. It will be bigger just because I have a bigger prompt coming in. And I'm saying this is going to stress your batching mechanism in terms of how many requests can I push into the GPU at once. If my pre-fill stage, that prompt processing stage, is efficient, I can see some higher throughput. So these are things that we look at a very granular level. If I have a long input and a long output, I would expect that time to first token to be big, or like bigger than a short prompt. My KV cache will just be storing more and more tokens because I'm storing the generated tokens. I'm saying it's going to stress your generation system because you're just filling up the GPU more and more. And you should expect to see less throughput in a scenario like this. This is where your cost really starts to go up in terms of people are just sending too much data into the system. This is why you get charged, per prompt. Short input, long output. My pre-fill stage is going to be small. I'm just going to do a lot more generation. And then lastly, this is a fast one. Both time to first token and generation should be really fast. And this is where you get the highest throughput from an LLM deployment. So rounding out, so at NVIDIA, we deploy our LLMs on this thing called Triton Inference Server. So this is a generic inference server. It hosts many different types of models. So I'm showing I can deploy a TensorFlow, a PyTorch, or TensorRT. That's a model format specific to NVIDIA GPUs. TRT LLM that I'll show you coming up. That's how we compile LLMs to NVIDIA GPUs. And this inference server manages all of the inference requests that are coming in, also the data going back out. If you are deploying LLMs on NVIDIA GPUs, highly encourage you to check out TensorRT LLM. And the main idea here is we've written a bunch of different CUDA kernels for all of these different language models. And you should expect to see sort of an increase in throughput and a decrease in latency. And what that does for you, it allows you to pack more requests per unit GPU to essentially optimize your cost. Quantization is something you do a lot when you go to optimize. Kyle will talk a bit more about that coming up. And that's just you reducing the precision of the math that's happening so that it happens faster and you get more math done per unit time. Lastly, as you start to think about which GPUs you're going to deploy on, I just kind of wanted to point out FP8 enabled GPUs. So FP8 enabled GPUs will actually reduce the memory and increase the speed of the math that you're doing. So that's something to consider. The GPU that you choose will sort of affect your speed. Tensor parallelism, this is where you split a model across multiple GPUs. You'll see Kyle talk about that. And that's what you're using to actually decrease the latency of your system. And if you've not checked out ai.nvidia.com, you can go play with all of these language models for free. I like to encourage people to go test out language models for their deployment. You get up to 5,000 inference requests for free for each person. And yeah, I'll hand off to Kyle.
All right, Kyle, I think you are live. Let's share your screen.
Well, thank you for the amazing, introduction, everyone, and thank you, Mark, for your presentation because it's really going to set up what I'm talking about right now. To start off with, I'm just going to be talking about deep learning systems at scale, and what that means is really how do we get models that we want to host, a number of models that we want to host, onto the hardware that we want to host in the most efficient way possible. And I always love to start with a little bit of history and just talk a little bit about what we're doing in NVIDIA to contextualize the discussion further on in the presentation. We had our first set of GPUs in 1999 with the GeForce 256. We were a gaming company at the time. We were doing a bunch of rendering. We, built more and more GPUs, culminating in probably one of the most famous gaming GPUs of all time, the GTX 980 Ti. And in 2012, we had our first deep learning model, which would be AlexNet. We followed, with many, many more deep learning models over time. We saw ResNet in 2015. And at the time, they were training on gaming GPUs. We evolved even more over time. We developed our first data center SKU, which was used to, because people would realize that you can actually use GPUs to do math and use that math to do deep learning. And then released our second data center SKU in 2017. But we started realizing that models kept getting bigger and bigger, and as Mark mentioned, we started experiencing things where we needed to basically represent models in parallel. The models got so large that we actually needed to think about a bigger unit of compute. And that started our commitment to the NVIDIA DGX series, which are a series of basically larger scale systems that use multiple GPUs in order to solve a specific problem. In 2018, after the release of our first DGX system, we saw the first GPT. In 2019, we saw the second. In 2020, we saw the third. And as everyone knows, we now have GPT-4. And we just kept getting bigger. We saw, our A100 SKU come out in the 2020, which is still a workhorse even today, 4 years later. And in addition to releasing just the S6M module and the DGX, we saw that there was a need for an even larger scale of compute because these models kept getting larger. And, instead of representing our model on just one node or one compute unit, we actually went to the data center scale and started building these things that we call superpods, which are 32 of a given type of node. Now, earlier in the presentation, Mark mentioned that we use different forms of parallelism to represent models. And the reason that we keep building larger and larger units of compute is so that we can do larger and larger forms of parallelism by connecting these smaller pieces of compute, like the GPUs, with communication hardware like NVLink or InfiniBand, and connecting them together so that you can actually combine the computation of multiple GPUs at once in order to infer something about or to perform inference. And in software, we've sort of been following the same hardware or the same abstractions that we've been following in hardware. So in hardware, we had the GPU and we built that into a DGX box, and then we built that into a superpod. In software, we build on top of CUDA. We build frameworks on top of it like PyTorch, JAX, and TensorFlow. We build communication frameworks that allow us to communicate between GPUs. And then we build, distributed building blocks like Megatron LLM and TensorRT. And then we integrate that at the top level in NVIDIA Inference microservices, which is what I work on. So what do we mean when we say AI at scale? Why do we need to keep building these larger and larger computers to even get inference done? Well, as Mark mentioned, we have ai.nvidia.com. And what AI at scale means to me generally is that we actually have a lot of models that we want to host and a lot of different types of compute that we can use to host them. So in our case, we're hosting models like Llama 3 or Mistral 8x22b Instruct or Gemma, which is a model from Google. And generally, what it looks like to me is we have a large amount of models that we want to host. We have a large number of instances or ways that we can host them, different locations and different SKU types. So as you can see on the right, we have different SKU types like the H100, A100, L40S. We also have different numbers of GPUs that we can include in those instances. Now, the core task of performing AI at scale to me is optimizing the mapping of these models onto these different types of hardware. And what that means really is you want to figure out what, given your constraints, are the most throughput per GPU you can get out of a given model. And in the end, it reduces to a table that looks something like this. The data center scale view of inference reduces to something like this, where you have a model that is running on a specific SKU with a specific tensor parallelism and pipeline parallelism and a specific number of replicas. And managing this type of deployment is generally focused around a couple of things. One, you need to understand the load that's coming in. This is an example of an actual load chart of the number of invocations of a specific function or for a specific model. You can see it follows some sort of regular pattern, which means that you as the user need to build a system that allows you to predict in the future what GPU demand is going to look like, and you also need to predict basically map your fleet of models to match that demand. So for example, if we've built a model for inference using a library like TensorRT LLM or TensorRT, we can test that model beforehand in order to determine its performance characteristics. When we talk about models, there's sort of a number of different characteristics that we sort of talk about. The first is just generally throughput, which is the number of tokens per second or images per second or units per second that your model can push out. So for LLMs, it's almost always measured in tokens per second. And I'll keep using LLMs as the example because they're probably the most complex. The other thing to consider is the latency on the user side. So as a user, there are a couple of different types of latency that you experience. One of them is just how long it takes for your request to get to the model, and that can depend on queuing. That is, are there people in front of you? Are you waiting for a worker to be available to take your work? And after it's queued, after your data has gotten to a specific worker, you actually have to pay in mind how long it's going to take for that worker to finish outputting the first token. Earlier, Mark mentioned a process called prefill, which is basically just how your LLM reads its input. So the time that it takes to essentially get to the first token is how long it takes for that model to do prefill, and then how long it takes to generate the first token. And generally, this is longer than the generation of any other token within the sequence, because again, you have to do both the generation of the prefill and KV cache filling, and then you also have to generate the first token. Whereas other tokens, the prefill and KV cache already exist, so you can just infer upon the next token. And the other metric, other than time to first token, which was mentioned there, is the intertoken latency, which Mark also mentioned, which is determined by basically the time it takes to get from token 1 to token 2 and the token 2 to token 3 and the average of that number. And as mentioned, that's a part of a general generation loop, which means you have to run the model every time to get a new token because it's autoregressive. In that case, those are the two key performance metrics that affect user experience, right? It's how many tokens per second a given model represented on a given number of GPUs can produce, and the latency of that model, the latency being broken into time first token and intertoken latency. In the case of total cost of ownership, which is a relatively important metric as well, we can compute the TCO on a per token basis, because again, you as a user actually want to be able to serve a number of tokens with a given model rather than just say, hey, what is the total cost of ownership of 10 replicas of this model that may or may not service a given amount of tokens. Essentially, with respect to TCO, we usually use a metric that's tokens per second over over the number of GPUs that it's being represented on. Because with tensor parallelism, you're using, or pipeline parallelism, you're using multiple GPUs to represent a model. And in this case, right, the more accurate metric is to normalize by the number of GPUs. So you can divide the total number of GPUs running on the system, you can divide the total number of tokens provided by the system by the total number of GPUs something is running on. And one other problem, that we encounter with respect to running these models is sudden increases in load. Again, you can't really predict for this. One of the biggest things that you can do to optimize the models in this case when you start running them is essentially to decrease the cold start time for your models. And what does that mean? So a model, when you're running it in a data center, requires a certain amount of time to download whatever microservice is used to represent the model, as well as download the model weights. And if you have demand that looks something like that, you obviously don't have that long to respond and wait for things to spin up. So if you were to, for example, download a model and then it's microservice fresh, what might be required in that case is to essentially download the whole thing, and that will take time, many minutes. So one of the things that you can do at a data center level is to pre-cache the models that you might need. So instead of having to download them from some remote artifactory, you can actually put the models and microservice that you need to use in your data center, so that when you need a new model or when you need to scale up more versions of the model, you can just access that cache and access it immediately. Now, there's an additional problem when we're optimizing at scale. So, Mark mentioned we have a couple of tools to optimize things, but generally that's under the assumption that we're optimizing for the same problem. A good example here is the input sequence length distribution of queries. Now, if you look at this, rough histogram I've thrown together, you can see an example of a distribution of queries. So, for example, to think about what the input sequence length distribution actually is, it's the number of tokens that are passed as input by the user, and that usually includes the entire history of the chat between the user and the model, as well as the prompt that you are currently making. So your history and the prompt that you made to the model. So for some applications, this can be very short. If you're just having a conversation with the model, it's likely that your input sequence length is not going to be very long, especially on the first set of queries. But you may end up with a distribution that has multiple modes, and actually may, if you separated it out, look like a number of different use cases that actually have their own unique distributions. So as you can see in this, we actually have three modes. There's the one at the left, the one in the middle, and the one at the top. And this is actually pretty normal for LLM applications. So you may have a bunch of short queries that represent users interacting with the chatbot in a conversational manner, a bunch of medium length queries that are, for example, providing zero-shot context or giving the model extra information about what they need from the query. And then you might have a bunch of extremely long context inputs that include things like articles you want to summarize, or even more context that the chatbot or application may need. And this is actually an interesting optimization problem, because obviously, if you build a system that's able to handle, or is built around handling, the short sequences, you likely are not going to get good performance with the longer sequences. And essentially, what this means is that actually in the data center, instead of representing a model with a single version, you actually may want to create multiple different versions of the model that are running on multiple different configurations. So instead of it being a question of just going back to an earlier slide, instead of it being a question of just which model is running on which SKU and how many of those SKUs, you actually make the decision about having a number of different configs for each model. So one config for a model may be compiled to be cheaper. And to go back to Mark's, Mark's discussion earlier, we can use parallelism to make models faster. However, generally, you can't get as good scaling as replica scaling, which is just to say, hey, if I were to create a model on 2 GPUs and create 2 versions of the same model on 1 GPU, those 2 versions of the model on 1 GPU would almost generally be able to provide more tokens per second on the total sum of those 2 GPUs. Whereas on the latency side, which is to say how fast, how fast you can, service a user's input. If you were to use 2 GPUs, the parallelism actually allows you to execute that operation faster. So you want to balance these 2 constraints. And in some cases, if you're dealing with different queries that have different user requirements or SLAs, you may want to have multiple configs in the model here. And generally, from an optimization perspective, considering both the SLAs that are presented to your user as well as the distribution of inputs that you're receiving informs you about whether or not you want to use tensor parallelism, what configuration of tensor parallelism you want to use, as well as the basically the targeted input and output sequence links that you want to be able to handle as a user. And that's about all I have. Thank you so much, everyone, for coming today. And I'm happy to hopefully be able to answer some questions.
Awesome. So that was really great, Mark and Kyle. Really, really awesome presentation. I'll also add Mark back as well because, got you back. So anyone do ask your questions. We do have a few minutes for Q&A. I do have questions for me that are prepared as well. Because this was covered a bit in the presentation. It's an interesting aspect about kind of how LLMs are evolving, especially today. There's often this conversation about whether scaling LLMs will lead to better performance, right? Whether more data, more parameters, right? But we're also seeing the advent of a lot of new small LLMs really focused on like specific use cases. So I'd just rather love to get your opinion. Kind of where do you see the field headed within the next 12 months? Do you see that small LLMs that are specifically designed for certain use cases? So for example, we saw Phi 3 released yesterday, has almost GPT 3.5 level performance, but can fit on a phone, right? Do you see that becoming more and more the norm, or do you see large scale foundation models becoming bigger and better, and that scaling is the path towards better performance? Maybe I'll start with you, Kyle, and then I'll go to Mark after that.
Yeah, sure. Where do we see models headed? We see a couple of interesting things, and I'm going to loop back to Llama 3, which was released last week because I've read the paper recently, and it's fresh in my mind. There are a couple of interesting trends that came out of that paper. One is we're absolutely going to see models continue to scale larger and larger and larger, right? Meta said that they're training that they released the 8B and 70B variants. And they've also said, hey, we also have a much larger model, a 400B model. It's also trained on the same set of 15 trillion tokens. And, that would indicate at an open source level, even we're going to continue to see larger and larger models.
Mm-hmm.
However, you're right. We are starting to get to the point where we have some models at a small scale that are extremely powerful and are reaching the levels that we saw initially in the rise of the chatbot boom with ChatGPT. So I see it going 2 directions. One, we're going to keep getting larger models that keep getting used in the data center for more and more maybe accuracy important applications. On the other hand, we're going to see smaller models start to develop, and we're going to be compressing models more with techniques like quantization, distillation, or pruning. And those will be used more in on-device applications like, Siri in your phone or a Google Assistant. And generally, we're going to see, sort of start to see this split where We have, the largest models in the data center that are used to handle very, very complex queries. And then you have the model on your phone that is used to handle very, very simple queries and may actually even call out to the larger model if it doesn't know the answer to something or is uncertain.
Yeah, that's really great. And then Mark, maybe your perspective, how do you see, do you want to add on top of what Kyle said?
Yeah, I think, for those listening, some chances are you'll have to deploy an LLM for work. And so there's what exists in work versus what exists in sort of projects that people do in addition to data security, et cetera, et cetera. So I think you'll continue to see this hybrid approach of I typically test with the big box APIs. So you get to see what maybe the hugest models sort of perform at. And then as folks start to think about sort of overall long-term deployments, they start testing out the smaller models. Naturally, they look to optimize costs with open source and smaller models, but I think on a query routing perspective, you'll see this hybrid approach where you almost have access to all LLMs at one point, whether or not you deploy them, and then you'll just make that query out. So it's interesting.
Yeah, that's really good. And I think this is kind of related to a question that we got from the crowd here that I'm going to paraphrase as well, because it's related to a question that I have as well. Person's asking like that they're working on a project of, financial analysis data, and they would like to kind of understand how to build an application that leverages large language models for this analysis data, for this financial analysis data. Maybe walk us through, Mark here, how would you approach building a pipeline today for these types of kind of applications, especially when you want to deploy a large language model? So how would you approach deployment of LLMs? And maybe if this is a better question for Kyle, I'll let you.
Either way,
direct it.
I think the main thing to keep in mind is where data is coming from and how that data gets to your model. So for instance, you might host a model on your machine, you pass in some data, and that's fine. But then when you go to a production system, what format is that data coming in? And as you start thinking about performance, what are the different conversion layers that you have to start happening from that perspective? In addition, if you have a RAG system and you're going to pull external data, now you have a bunch of different parts that are working to get data into your LLM to get a corresponding output. If you do have guardrails and all that stuff, you'll have to add an extra module on top of that. Some things we're seeing folks doing is using LoRa's to kind of act as guardrails. So that LoRa is that extra little module on your base model that will circumvent certain things happening, or it'll add sort of extra functionality. So to summarize, meaning make sure that your input data format is going to be the same during your pilot building as it is going to be into production. You'll have some API that pushes the request into your LLM, hosted as some microservice or some API call to a big model or a small model, and then you take that output, do your post-processing. I think you'll have to write some code to do some post-processing as well, and then push it out. Consider where your data is written to as well. That writing speed.
That's great. And maybe one final question as well, given that we're almost at time, is this question from Isis Barrett Lally. She is asking, great question here. What do you think of the potential of using model-generated data to train large language models, specifically for small models? Kyle, maybe I'll start with you.
Yeah, using larger models to bootstrap smaller ones is certainly something that is very common at this point. We saw early on one of the Llama variants bootstrapped by GPT 3.5 when they created the Vicuña model. However, one of the things that we do need to be careful with is the fact that from a commercial perspective, a lot of the large models do not allow you to use their output as training data for other models. So it's going to depend on which model you're using, if you're considering something for commercial applications, because I believe that using large model outputs for research, for research on training of smaller models, as long as it is released under a research license, is still okay. Maybe check that. Don't cite me on that. And one other thing that was really interesting from the Llama 3 paper that was super cool from my perspective is actually not creating synthetic data, but they used Llama 2 to basically determine the quality of data and use it as a filter for
Mm.
the training set for Llama 3, which is another way of utilizing a model to sort of even bootstrap itself in a weird, sort of weird way.
Yeah, that's very fascinating. It's going to be interesting to see, how this evolves. Now we have a few extra questions to ask, but I do want to be mindful of everyone's time here. So everyone, do reach out to Mark and Kyle for any additional questions that you get. Their LinkedIn is on the event if you're on LinkedIn, or reach out to them wherever you find them. I want to say a huge thank you both for Mark and Kyle for joining us, for NVIDIA for partnering with us on this webinar. But also for everyone who attended this webinar today. Quite a few people from all over the world, different time zones. It's really an honor. Mark, Kyle, really appreciate you joining in.
Fantastic. It was fun.